Hello everyone. Today we will discuss about Nyquist stability criterion. Nyquist stability criterion is used to check the stability of closed loop system from the knowledge of the open loop transfer function. So my aim is to determine the stability of a closed loop system if I know the open loop transfer function. So consider this system having input R of s and a response C of s. The open loop transfer function of the system is given by g of s into h of s. Let's assume that g of s into h of s is of the form s minus z1 into s minus z2 into s minus zm divided by s minus p1 into s minus p2 up to s minus pn. That means that the open loop system is having m zeros and n poles. If I write the closed loop transfer function, which is of the form g of s divided by 1 plus g of s h of s, it will look like g of s divided by 1 plus, and I have the value for g of s h of s as s minus z1 into s minus z2 up to s minus zm divided by s minus p1 into s minus p2 up to s minus pm. Taking LCM and taking the denominator to the numerator, I will get it as g of s into s minus p1 into s minus p2 up to s minus pm divided by s minus p1 into s minus p2 up to s minus pm plus s minus z1 into s minus z2 up to s minus zm. Also, the characteristic equation of the system can be written as 1 plus g of s h of s equal to 0. That becomes s minus p1 into s minus p2 into s minus pn plus s minus z1 into s minus z2 up to s minus zm, the whole divided by s minus p1 into s minus p2 up to s minus pn. So here I have written the open loop transfer function, the closed loop transfer function, and the characteristic equation. Comparing these transfer functions, I can say that the poles of the open loop transfer function, which are p1, p2 and pn, and the poles of the characteristic equation, they are p1, p2 and pn, are same. That means that the open loop transfer function and the characteristic equation are having the same poles. Both of these equations, that is g of s h of s and 1 plus g of s h of s, is having the same poles p1, p2 and pn. And if I take the zeros of the characteristic equation, the zeros of the characteristic equation is obtained by equating the numerator of the characteristic equation to 0, that is s minus p1 into s minus p2 up to s minus pn plus s minus z1 into s minus z2 up to s minus zm. This should be equal to 0. And if I check the denominator of the closed loop transfer function, I can find that the denominator of the closed loop transfer function is same as the numerator of the characteristic equation. So I can say that the zeros of the characteristic equation is same as the poles of the closed loop transfer function. So in order to analyze the stability of a closed loop transfer function, we need to know the location of poles of the closed loop transfer function, which is given by the denominator of the closed loop transfer function. So in Nyquist stability criterion, instead of finding the location of the poles of the closed loop transfer function, I will looking forward to find out the location of zeros of the characteristic equation, because both are same. So in Nyquist stability criterion, I will be checking the location of zeros of the characteristic equation to determine the stability of the open loop transfer function. So if I know the location of zeros of the characteristic equation, I can say that I know the location of poles of the closed loop transfer function. So if the closed loop transfer function is having any pole on the right half of S plane, then I can say that the system is unstable. Or I can say that If the characteristic equation is having any zero on the right half of S-plane, then the closed loop system is unstable. Okay, so here are some conclusions. Poles of the open loop transfer function and poles of the characteristic equation are same. Poles of the open loop transfer function and poles of the characteristic equation are same. We have seen that. Zeros of the characteristic equation are the poles of the closed loop transfer function. That is, the numerator of the characteristic equation and denominator of the closed loop transfer function are same. That means that the zeros of the characteristic equation are the poles of the closed loop transfer function. So, by looking at the location of zeros of the characteristic equation, we can predict the stability of the closed loop system. So, if I know the location of zeros of the characteristic equation, I can say that the system is stable or not. If the characteristic equation has zeros on right half of S-plane, then the closed loop system is unstable. If the characteristic equation has zeros on the right half of S-plane, then the closed loop system is unstable. For a closed loop system to be stable, its characteristic equation should not have zeros on the right half of S-plane. So for a system to be stable, the characteristic equation should not have zeros on the right half of S-plane. That in turn means that the closed loop transfer function should not have poles on the right half of S-plane. So now let's get into some of the maths needed for Nyquist stability criterion. So I'm assuming I'm having a function of f of s, where s is the complex frequency given by sigma plus j omega, and I'm representing the s variable in a plane called s plane given by a real axis sigma and an imaginary axis of omega given as sigma plus j omega. Each point will give certain value for sigma and certain value of omega. So you can say that the value of s will be a complex number, and if I substitute that value of s, the complex number, in the function f of s also going to be a complex number. So s is a complex number, hence f of s also will be a complex number. So let's assume that S plane, I am taking a point here which will be having certain real value and certain imaginary value, and if I substitute this value into f of s, the function f of s, I will be getting a value for f of s which also will be a complex number. That means that also will be having a real part and imaginary part. Such an f of s value I am plotting in a plane called f of s plane, which is having a real axis and imaginary axis. So I will be getting a point in the f of s plane. That means that every point in the s plane can be mapped into f of s plane. So whichever value of s I take on the s plane, I will be getting corresponding value in the f of s plane. So if I take large number of points, if I take large number of points in the s plane to form a curve, it will be mapped as another curve in the f of s plane. So if I am taking a curve in the s plane, it will be mapped as another curve in the f of s plane. And if I take a closed path in the s plane, it will be mapped as a closed path in the f of s plane. If I take a closed path in the s plane, and if I map each point of the closed path to the f of s plane, this is f of s plane. So that means that a closed path in the s plane is mapped as a closed path in the f of s plane. So I'm taking the same function f of s, and I am assuming that if I put f of s equal to 0 as a function, that means that the function will give some poles p1 and p2, and the function, let's have the function has a 0 z1. So let it be like don't take f of s equal to 0. Let it be like if I have function f of s which have poles p1 and p2 and 0 z1. It is having two poles p1 p2 and 1 0 z1. And I have mapped those poles and zeros in the s plane like this. Here I have p1, here I have p2, and here I have z1. And I am taking a closed path in the s plane in such a way that the closed path encloses or encircles only p2. Now I take a point, arbitrary point x in the closed path, and I draw vectors from all these singular points, that is p1, p2 and z1, to this point x, such that when this point x moves along this closed path, all these faces will change its angle. And I can see that the phasor of p2 will move around this closed path. When I reach back at the same point, it should have rotated through 360 degree or 2 pi radian. But I look into the phasors from p1 and z1, I can see that the net angle change by the phasor of p1 will be 0, as the phasor from p1 moves forward and backward. It is not rotating. It comes back to the original phasor position as the point x moves from x and back to x. Similar is the case from z1. The net phase change of phasor of p2 will be 2 pi as it rotates. The net phase change of phasor of p1 will be 0. Net phase change of phasor from z1 also will be 0. So I have some conclusion. The f of s contour, that is the mapping of this closed path in the f of s plane, is also going to be a closed path that we have discussed earlier. If I am taking a closed path in the s plane, then the mapped contour in the f of s plane also will be a closed path. So I have a closed path in here, so mapping is going to be a closed path for sure. The f of s contour will encircle the origin in the clockwise direction by an angle given by the f of s contour will encircle the origin in the clockwise direction by an angle given by sum of phase changes of phasors of all zeros, sum of phase change of all phasors from zeros, minus sum of phase change of phasors of all poles. That means here I have only one 0, and the net phase change of the phasor of this 0 is 0 degree. So there is the sum of phase change of phasors of all zeros will be 0, because I have only one 0 over here, and the phasor of this 0 rotates only 0 degree. Net phase change of this phasor is only 0 degree. So I have 0, I have no other phasor from zeros, and minus sum of phase change of phasors of all poles. So I have one pole over here and one pole over here. The phasor from P1 rotates through 0 degree, and phasor from P2 rotates 2 pi degree. So 2 pi plus 0 gives minus 2 pi. That means that f of s contour will encircle origin in clockwise direction minus 2 pi radian. That means that it is actually encircling the origin in anti-clockwise direction. That is one anti-clockwise encirclement. Okay. We shall see it in detail. These are given by principle of arguments. For a mapping f of s from S plane, if the selected region in the S plane has Z zeros and P poles, that is, I am selecting a closed path in the S plane, and if the closed path encloses Z zeros and P poles, then the f of s contour in the f of s plane will encircle the origin n is equal to z number minus p times in clockwise direction. I'll repeat. If the selected region in the S-plane encloses z number of zeros and p number of poles, then the f of s contour will encircle origin in clockwise direction how many times? N is equal to z minus p times. So